And welcome back as we continue our cosmic journey through our own solar system. We are now going to look at our next type of celestial body, which is that of asteroids. So let's start off by first talking about the discovery of the asteroids, because while the planets were easy to observe, asteroids were a more recent discovery by comparison. Asteroids are mostly found, of course, between Mars and Jupiter, a region of the solar system that we refer to as the asteroid belt. Now, asteroids are too small to be seen without a telescope, which is one of the reasons for their late discovery. In the late 1700s, astronomers were hunting for a planet they thought should exist somewhere between the orbits of Mars and Jupiter. Now, the Sicilian astronomer Giovanni Pazzi thought he had found this missing planet in 1801 when he discovered Ceres orbiting at 2.8 AUs from the Sun. His discovery was quickly followed by the detection of 3 other little planets in similar orbits. Of course, this then started leading to further discoveries about this area between Mars and Jupiter. By 1890, more than 300 of these minor planets, or asteroids as they were starting to be referred, had been discovered by sharp-eyed observers. And by 1890, Max Wolf introduced astronomical photography to the search for asteroids, greatly accelerating the discovery of these dim objects. In the 21st century, searchers then used computer-driven electronic cameras, which was another leap forward in technology, allowing us to map even more of these objects out here in this space between Mars and Jupiter. Now currently, many asteroid searches are made with cameras that are actually located out deep in space, and we've actually mapped more than 1 million asteroids into their kind of well-determined orbits around the Sun. So, as we start talking about these orbits of the asteroids, you have to understand, all revolve around the Sun in the same direction as the planets, and most of their orbits lie near the plane in which Earth and other planets circle. The majority of the asteroids are in the asteroid belt and have orbital periods between 3.3 to 6 years. Now, although more than 75% of the known asteroids are in the belt, they are not closely spaced together. The volume of the belt is actually very large, and the typical spacing between objects is several million kilometers. So when we start looking at the asteroid belt, one of the first things we can start wondering is, where did the asteroid belt come from? What is it made of? And so looking at those things can help give us clues to the early solar system. So when we talk about the composition of asteroids, they are typically broken into 3 different classes based upon their compositions, or what they're made of. The dark asteroids are called C-type asteroids, or carbonaceous. These are revealed from spectral studies to be primitive bodies composed of silicates mixed with dark organic carbon compounds. Now, 2 of the largest asteroids, Ceres and Pallas, are considered to be primitive asteroids, as are almost all of the asteroids in the outer part of the belt. The second most populous group is the S-type asteroids, which are stony or silicate composition. The dark carbon compounds that we find in C-types are missing, resulting in a much higher reflectivity and clear spectral signatures of silicate materials. The S-type asteroids are also chemically primitive, but their different composition indicates they were probably formed at a different location in the solar system than that of the C-type asteroids. And of course, then we have a third type, which is our metallic asteroids. Asteroids of this third class, which are much less numerous than the first 2, are composed primarily of metal and are called the M-type asteroids, or metallic. Well, how did such metal asteroids come to be? Well, we suspect that each of these metal asteroids came from a parent body large enough for its molten core interior to differentiate, and the heavier metals sank to the center. When this parent body shattered in a layered collision, the fragments from the core were rich in metals. In fact, there is enough metal in even a 1-kilometer M-type asteroid to supply the world with iron and many other industrial metals for the foreseeable future, if we could bring one safely back to Earth and not cause catastrophic destruction. So where different types of asteroids are found in our solar system really kind of varies. Asteroids of a different composition are distributed at different distances from the Sun. As you recall, the S-type and C-type are both primitive type, and the M-type consists of cores from differentiated parent bodies. By tracing how asteroid compositions vary with the distance from the Sun, we can actually reconstruct some of the properties of the solar nebula from which they were originally formed. So, for example, we look here at this graph. We can see here in their distance from the Sun, the stony type are actually found closest to the Sun. The metallic types are a little bit more here in the middle, and the C-type are typically found the farthest out. So that, of course, gives an interesting distribution of looking back and saying what was or what could have been potentially a body that was out here in this distance between Mars and Jupiter. So with that being said, let's look at Vesta, which is a differentiated asteroid, because we did talk about how some of these metallic asteroids probably came from differentiated primitives. Well, Vesta is a very interesting asteroid. It orbits the Sun with a semi-age axis of 2.4 AU in the inner part of the asteroid belt. It has a relatively high reflectivity of almost 30%, making it one of the brightest asteroids that we can see. Now, its surface is covered with basalt, indicating that Vesta is a differentiated object that must once at least have been volcanically active, in spite of its small size, only about 500 kilometers. Now, meteorites from Vesta's surface, identified comparing their spectra with that of Vesta itself, have landed on Earth and are available for direct study in the laboratory. The age of the lava flows from these meteorites derived has been measured at 4.4 to 4.5 billion years, which is very soon after the formation of the solar system. Now, this age is consistent with what we might expect for volcanoes that would have been on Vesta. Well, that's enough information about some of the stuff about asteroids and some of their compositions, but what do they actually look like? Let's try and see if we can get up close and personal with a few of these asteroids. Now, on the way to its encounter with Jupiter, the Galileo spacecraft was targeted to fly close to two main belt S-type asteroids called Gaspra and Ida. The camera revealed both as long and highly irregular, as befits fragments from a catastrophic collision, because in a collision things are going to fragment off into weird irregular shapes. So scientists conclude that these asteroids are only about 200 million years old. Now, the greatest surprise to the Galileo flyby of Ida was the discovery of a very tiny moon in orbit around the asteroid. Also pictured in this image, you can see Math&Comps, a C-type asteroid, which was a near flyby target for the Near-Shoemaker spacecraft. And you can see how it has almost more of a rounder shape rather than some of this more irregular shapes that we see here with Gaspra and Ida. Now, an interesting thing about asteroids, and we mentioned this before when we started talking about them, is that sometimes they might have actually ended up as captured moons of planets. Let's look at Phobos and Deimos, which are the two small moons of Mars, and they're actually most likely to be captured asteroids. If we look at the shapes of them, they're both kind of irregular, somewhat elongated, and heavily cratered, resembling other smaller asteroids. Now, their surface dimensions are about 26 kilometers and 16 kilometers respectively, so they're pretty small. Their surface materials are also similar to many of the asteroids that we find in the outer asteroid belt, leading astronomers to believe that the two moons are most likely captured asteroids. Now, the small outer moons of Jupiter and Saturn were probably also captured asteroids, perhaps early in the history of the solar system. And this is something that we believe because remember, one of the things we also talk about is some of these captured asteroid moons have a retrograde orbit in respect to the other moons, and so that's part of the reason why we believe that they might have actually just been captured by some of these larger planets. So with that in mind, we have an inkling to want to study asteroids to kind of figure out their history and where their places in the formation of our solar system. Well, the Near-Shoemaker spacecraft orbited the Eros asteroid at various altitudes, measuring its surface and interior composition, as well as mapping Eros from all sides. Now, several other asteroids are loosely bound rubble throughout, but interestingly enough, Eros has a uniform density and extensive global scale grooves and ridges so that it is a cracked but a solid rock. The top of loose soil is dotted with scattered half-buried boulders. Now, Japan's Hayabusa 1 mission studied the S-type asteroid Itokawa, which is much smaller than Eros and only about 500 meters long. And you can notice with this asteroid, it's a little different looking than what we saw with Eros. This asteroid is much more elongated and appears to be a result of the collision of two separate asteroids long ago, and they kind of fuse together. You can kind of almost see here where you have two different pieces that kind of met and fused together. Now, there are almost no impact craters here on this asteroid, but we do have an abundance of boulders, kind of like a pile of rubble on the surface, and you can see all these kind of dotting along the surface here, giving kind of this rougher exterior in comparison to that of Eros. Now, one of the interesting things about the survey is it also collected a small sample of materials from the surface, and that sample materials was estimated to be about 8 million years old, indicating that this is a relatively fresh surface. Well, that's pretty cool, but how close can we get to an asteroid? Can we actually land on one? Well, this would happen when we went and explored the asteroid Bennu, which is a small half-kilometer diameter, rapidly spinning dark asteroid. Now, the low density of Bennu suggested that it was a loosely bound rubble pile, just a pile of rocks pretty much held together by gravity. Now, the surface of Bennu is very rough, with protruding rocks and boulders. As part of the mission OSIRIS-REx, a probe collected a sample of the surface, and the collection arm is shown here in image B, just before touchdown on Bennu. Just for scale, the diameter of the sampling device is 30 centimeters. So think about that as, kind of like the size of a ruler. That's about how big that sampling arm was. Now, the sample of about 100 grams of surface rocks and dust was then returned to Earth in 2023 and is now being studied as they look at the different makeup of the different particles that existed here on Bennu. But, of course, we can't talk about asteroids without, of course, talking about some of the largest, Ceres and Vesta. The Asteroid Space Mission Dawn has visited the two largest main belt asteroids, Ceres and Vesta, orbiting each in turn for about a year. Their large sizes make them approved for comparison with planets and large moons. Both turned out to be heavily cratered, implying their surfaces are pretty old. On Vesta, we have now actually located the large impact craters that ejected the basaltic meteorites previously identified as coming from this asteroid. And when we look at Ceres, Ceres has not had a comparable history of giant impacts, so its surface is covered with craters that look much more like those that we would find in the lunar highlands. Now, lastly, we, of course, had an interstellar visitor, because while we mostly think about asteroids as existing between Mars and Jupiter, they, of course, can exist in other locations. In late 2017, something entirely new was discovered, an interstellar asteroid. This visitor was found at a distance of 33 million kilometers from where we would expect to find things. As astronomers followed up on the discovery, it quickly became apparent that this asteroid is traveling far too fast to be part of the Sun's family of asteroids. And another thing that was interesting, instead of being the normal kind of elliptical orbit that we would see, we actually found its orbit to be more of a hyperbola. And when it was discovered, it was already rapidly leaving the inner solar system. As we learned that planetary systems are common, as we're doing more and more of our deep space exploration, the question starts forming. And we start asking, where are similar debris objects ejected from planetary systems? What are the causes of these things? What are the reasons that an asteroid might be pulled from one system and be yanked into another? And so this allowed us to rethink some of our models of what might be able to be captured or rejected from within a single star system.